This is the end. Here we are, lesson 11-9. You should have your book. Celebrate with your book. Page 618 is where you can turn in your book. We are finally going to solve rational equations. Start at the very beginning. A very good place. Let's go red. Hardcore. Yeah, so we're going to solve rational equations. A rational equation just means that it is an equation. It has an equal sign and a rational expression in it. And typically what we mean by rational expression, by now I presume you know, is that we have a variable, especially variable somewhere in a denominator. For this first one, we have 12 over x plus 5 equals 4 over x plus 2. And the book doesn't specify this. It doesn't get into this till the last example, which seems super backwards to me. The very first thing we should be doing when we solve rational equations is make sure we know what our excluded values are. Remember, there are certain values that because we have variables in the denominator, we cannot let that variable equal. Anything that would cause a denominator to be 0 would cause one side of the equation, if not both, to be undefined. And that's no good. That means we don't have a true solution whenever that happens. So we want to watch out for that from the very beginning. And so what I'm going to do first here is I'm going to look at x plus 5 and x plus 2, my two denominators, and I'm just going to write down to remind myself, okay, so that means x cannot be negative 5, because in that case, this denominator would be 0. And x cannot be negative 2 for the same reason. This other denominator would then be 0. Now, maybe that's not going to matter, right? Maybe we're going to do some solving right now. We're going to get x equals 11, which means that whether or not the fact that it's not negative 5 and it can't be negative 2 makes no difference to me. But just in case, we want to have it written down from the beginning. So that's what I did here. After that, we have a few strategies. Now, our main strategy later on in this lesson is going to be common denominators. We need common denominators to be able to add and subtract rational expressions. So anytime we have these rational equations with plus or minus signs, chances are we're going to need a common denominator. But example 1 here is actually an exception to that, because you should be looking at this and thinking to yourself, man, that's funny. This looks a lot like a mathematical object we have worked with before. What happens when we have ratio equals ratio? Or, blank over blank equals blank over blank. What do we call that? We call that a proportion, right? And so typically when we have proportions, we want to find our cross products to be able to solve. And that is exactly what we're going to do here. We are just going to say 4 times the quantity, x plus 5, if this is going to have a solution, needs to be equal to the other cross product, 12 times the quantity x plus 2. From there, of course, we want to distribute. We're going to distribute a 4 on the left and a 12 on the right. So that is 4x plus 20 equals 12x plus 24. You'll notice at this point, we wouldn't consider this a rational equation anymore. This is just a normal linear equation. It's got variables on both sides, but that's no problem for us because we are, here at the end of the year, Algebra Masters. We use our subtraction property of equality, SPO. Do you guys remember SPO? Oh, gosh, the memories are just flooding back to me. 20 equals 8x plus 24. Subtract 24, subtract 24. Negative 4 equals 8x. Divide by 8, divide by 8. Getting a little low here. Sun's getting a little low, buddy. X equals negative 1/2. We do a quick check back. Was that one of our excluded values? No? Then we are happy, right? That is what we would consider a true solution. So again, I wouldn't say that this is a strategy we can go to every time for solving rational equations, but if our rational equations happen to just look like a proportion, then solve it like a proportion using your cross products. Take a moment and work out both. Check your progress 1A and 1B using the same technique. All right, so there you have it. I didn't quite do it in order. I didn't do my excluded values till later in the process, but nevertheless ended up with true solutions in both cases. Y equals -4 is what I got for Check Your Progress 1A. Pretty sure I did that correctly. F equals 20/89 is what I got for Check Your Progress 1B. Definitely made me think I did something wrong, but I actually don't believe that's the case as I look back at it and I check my work. Seems to be working out. It's just a weird solution. Maybe something went wrong when they were writing the question. I don't know. 13 times 7 is 91 there. Anyway, that's Check Your Progress 1A and 1B. Let's move right along into example 2. And this one is going to be our primary technique using a least common denominator or least common multiple. So here's what it looks like on example 2A. We've got n minus 2 over n. And we're subtracting n minus 3 over n minus 6. And this whole thing is equal to 1 over n. As I look at this, hopefully what you're noticing is two of the denominators are already common, right? N and n are the same thing. But then this other denominator is not merely 6 less than that n. I mean, it is that, but it's a totally different factor, n minus 6. And as we said in the last lesson, typically the easiest way to come up with a common denominator is just to use both of the factors. In other words, as I look at this n, what is it missing? Well, it's missing the n minus 6. As I look at this n minus 6, what is it missing? Well, it's missing the n by itself. Remember, these are different factors. We can't just add or subtract to come up with common denominators. We have to multiply. That's why it's called a least common multiple, right? And then n, same thing we did over here on the left. We're going to multiply by n minus 6. But all of these are incomplete because, of course, we're not allowed to just multiply random parts of the equation by different values. The only reason we're allowed to do this is because what we're going to multiply by needs to not actually affect the fraction or the rational expression. It just affects what it looks like. In other words, we are going to multiply by a form of 1 in each case. So that's n minus 6 over itself for the first and last expression, and n over n for the middle expression. You can see that's going to require quite a bit of multiplication on our part, like this n minus 6 times n minus 2. You might need to use box method. I'm so glad box method came up in the last lesson. Just, man, the callbacks tonight. We may need to use, let's do a nice little box method for old time's sake. How did we multiply? N minus 6 times n minus 2. N squared minus 6n minus 2n. Plus 12. Like terms along that diagonal, classic. N squared minus 8n plus 12 is going to be that new numerator. Oh, the memories. Okay, so there we have it. N squared minus 8n plus 12 is the product of n minus 6 and n minus 2. Now in the denominator, you could multiply it out the same kind of way with box method, or here distribution would work just as easily, but we don't need to. In fact, we really, really don't need to. I already said in the last lesson we don't need to, but we're going to see here in a second, again, we really, really don't need to in this lesson. For that next fraction, it is just going to be distribution, so that's going to be n squared minus 3n. And again, the whole thing, I'll just keep writing the same denominator. And then here, we are technically distributing, but we're distributing a 1. So it just becomes n minus 6 over n minus 6 times n. Multiplication, of course, is commutative. So you'll notice I flipped the order around for some of these denominators, but that's fine. That makes no difference. Okay. So what am I talking about? But we don't need the denominators anymore. Once I have everything over a common denominator, imagine a fraction problem like 7 over 8 minus x over 8 equals, let's do 3 over 8. So we have a common denominator. Can you tell what x is here? 4, right? I would bet a lot of money. None of you said, oh, it's 4 over 8. or it's 1/2. X is 4 here, right? And I don't need the denominator to know that. I just need to know 7 minus something is 3. What's the something? It must be 4. Notice if the problem were completely different. Let's say it was 7 over 99 minus x over 99 equals 3 over 99. What's x now? Is it 4 over 99? No. It already has an over 99 part. The fact that all three of the fractions happen to be over 99, I mean, it makes my job easier, right? It means, once again, all I really care about is 7 minus something is 3. That something must be 4. So notice in either of these two cases, as long as I had the same denominator across all three fractions, it didn't make a difference what that denominator was. And so I'm going to do a similar kind of thing with this problem here. I'm actually going to ignore the denominator entirely. I'm just going to start rewriting n squared minus 8n plus 12. Now I do have to make sure I'm subtracting everything in that second expression. So that's minus an n squared plus a 3n, because essentially I'm distributing that negative sign, right? Equals, and then over here, n minus 6. You'll notice at this point I have some like terms that combine. N squared minus n squared becomes 0. Negative 8n plus 3n become negative 5n. The plus 12 doesn't go anywhere. And again, the whole thing is equal to n minus 6. From here, I might start bringing my n's over. 12 equals 6n minus 6. Adding my 6. 18 equals 6n. Divide by 6. Divide by 6. 3 equals n. Now, I've been a bad boy. I did not identify my excluded values first. So I might come all the way back up here and ask myself, well, what can n not equal from that first thing? N cannot be 0. From that second factor, n cannot be 6. And of course, this one would also be n cannot be 0, but we don't need to do that because we already wrote it down over here. As I check this, this is not 0 and it's not 6. And so I'm good to go. That really should work. That is a true solution. Let's do another one of those. I know that's probably a little bit strange to you. Example 2b, we've got negative 4 over a plus 1 plus 3 over a equals 1. Now, again, one of the things that you're going to have difficulty with is trying to convince yourself, why can't I just add 1 to the numerator and the denominator of that second fraction? I mean, just think of any fraction. Let's say it was like 3 over 8. But for some reason you wanted to turn it into something over 9. Could you just add 1 and say, oh yeah, 3 over 8 is the same as 4 over 9? No, 3 over 8 is 0.375. 4 over 9 is 0.444, repeating. Or if you did it again, let's add 1, you would get 5 over 10. Is this the same as 0.5? No, right? You cannot change fractions by simply adding something to the numerator or the denominator. What you have to do is make sure that they have a common multiple. That is, you're going to be multiplying things. And so I just look at the different ones. A plus 1 is different from a, difficult though that is to imagine. 1, I also want to make sure is expressed as a fraction. 1 over 1 is what I'll call it. What additional factor do I need in that denominator for the first fraction? I need a. But I'm not changing anything, so I make it a over a. What additional factor do I need in that second fraction? A plus 1. But I don't want to change anything, so I make it a plus 1 over itself. What do I need for the 1? I need both of them. I need an a and an a plus 1. And of course, I want to make sure that I'm doing it for both the top and the bottom. So remember, we are multiplying here, so that gives me negative 4a over my common denominator, which I know is not even going to matter here in a second. Little distribution for the second rational expression, 3a plus 3 over a times a plus 1 equals, a little more distribution, a squared plus a over a times a plus 1. I only care about my numerators. Negative 4a plus 3a is negative 1a plus 3 equals a squared plus a. And then if I have a quadratic, I want my zero product property. Another old friend, come back for the finale. I'm going to get a 0 on that side. 0 equals a squared plus 2a minus 3. That factors as a plus 3, a minus 1. And then finally, where will a plus 3 equal 0? At negative 3. Where will a minus 1 equal 0? At positive 1. Again, I forgot to do my excluded values. As I go back, I can see a cannot have been 0, and a cannot have been negative 1. But since neither of these is 0 or negative 1, we're good to go. Both of these are true solutions. Try this out yourself on Check Your Progress 2A and 2B. There you have it. There is my work for Check Your Progress 2A and 2B. You'll notice I'm not even computing the denominators anymore. I'm just calling them CD, which stands for compact disk. No, it stands for common denominator. And so once I have that common denominator, don't need it anymore, combine just the tops using, of course, subtraction. I eventually get 4 equals 4b, so b equals 1. Over here, I need a c and a c plus 2. You'll notice I immediately factored the denominator of that first expression, and then eventually worked my way to a quadratic. C squared plus 3c equals 28. Zero product property, subtracted that 28 from both sides, factored it, and then solved. C equals -7, c equals 4. My excluded values were 0 and -2. Since neither -7 nor 4 is 0 or -2, we are good to go. So how about it? Let's look at example 3. Now, I mentioned in my little note on the homework that I would not recommend doing it the way the book says to do it. And I don't. I mean, it's not the worst thing in the world, but I feel like they're trying really hard to turn this into a rational equation. So here's how I would approach it. It takes Abby 2 hours to mow and trim Mr. Morley's lawn. When Jamal worked with her, the job only took 1 hour and 20 minutes. How long would it have taken Jamal to do the job himself? So here's the thing. There are 3 different rates in this question. There is the rate for Abby by herself. I'm going to call that RA. There is the rate for Jamal by himself, which is what we're interested in, right? That's the question. And then, of course, there is the rate for them working together, which I'm going to call R sub A plus J. So Abby's rate we're actually given directly. We're told it takes Abby 2 hours to mow and trim Mr. Morley's lawn. So a rate, remember, typically it comes from rate times time equals d for distance. Or sometimes we write it this way, rate times time equals work. That is, when you multiply a rate times an amount of time, you get some job done at the end. This means that rate is the job per some period of time. In this case, I'm literally just going to call it one lawn, right? That's the job that she does. And she's able to do it in 2 hours. And if I simplify this, of course, I get that means she is working at 1/2 lawn per hour. So let's move this stuff over a little bit. We don't know Jamal's rate by himself, so I'm going to skip that. But we do know that when they're working together, it only takes 1 hour and 20 minutes. Well, a little math over here real quick. 1 hour and 20 minutes. 20 minutes is how much of an hour? A third, right? 20 over 60 is 1/3. And so that's really the same as 4/3 hours, right? All of these are the same. So coming back over to their work together, they together complete one lawn in 4/3 of an hour. How do we divide by How do we divide by fractions? This was all, it's something you've learned years ago, but also definitely important in the last lesson. We multiply by reciprocals, right? And so this is really 3/4 of a lawn per hour. Now finally, let's think about what's going on here. If by herself, Abby can do half of a lawn in an hour, but together they actually did 3/4 of a lawn in an hour, what must Jamal have been accomplishing? The difference between the two rates, right? In other words, this is a sum. Abby's rate plus Jamal's rate is going to equal their combined rate, their work together, right? And so Abby's rate, again, we figured out was half a lawn per hour. We don't know Jamal's rate, but when they worked together, it was 3/4 of a lawn in an hour. And so if we subtract the 1/2, subtract the 1/2, we get that Jamal, all by himself, must be completing 1/4 of a lawn per hour. Now, you want to be careful about how you state this. It says, how long would it have taken Jamal to do the job himself? So let's come back to our R times T equals work equation. If Jamal's rate was 1/4 of a ln per hour times some amount of time we don't know, and that equaled 1 ln, how would I solve this for T? What would I do to get rid of that 1/4? Well, we would want to multiply by the reciprocal, right? 4/1. These cancel, leaving me with T. And over here, 1 times 4/1 is 4. In other words, if Jamal can do 1/4 of a ln in an hour, then of course he can do 1 full ln in 4 hours, right? And so that's why the answer to this question is 4. And so really my little, not an innovation, that's not the right word, but my little method here is all about stating their rates as some kind of sum or difference with each other. When people work together, it would be a sum of the two rates. Let's just do check your progress number 3 together, because I imagine that's a little bit strange. Lupe can paint a 60 square foot wall in 40 minutes. Working with her friend Steve, the two of them, Steve Rogers? The two of them can paint the wall in 25 minutes. How long would it take Steve to do the job himself? Capital J in my book, Book of Job. First of all, the 60 square foot thing is a complete red herring. Logic. My gosh, this lesson has everything. It's a job. Every time we do this, we're thinking one job. Lupe's rate, so that's RL, is this one job. I mean, I guess you want to call it one wall per 40 minutes. And so that's the same thing as 1/40th wall per minute, right? And then Steve by himself, we don't know, right? That's the question. But together, so L plus Steve, we can say that they can complete the one wall in 25 minutes, or 1/25th wall per minute. Well, again, if we set this up as an algebraic equation, 1/40th plus Steve's rate should be equal to 1/25. Subtract your 1/40th, subtract your 1/40th, and you get that Steve's rate is going to be 1/25 minus 1/40. Both of these have a common denominator at 200. So I'm multiplying this by 8/8. I'm going to multiply this by 5/5. So we get 8/200 minus 5/200 equals 3/200 walls per minute. Remember, R times T equals work. So Steve's rate, 3/200, times some amount of time equals the one wall that we're trying to complete. Multiply by your reciprocal, 200/3. And that means that the amount of time, which remember was denominated in minutes up here, the amount of time Steve would take would be 200 thirds minutes, or 3 goes into 200, 66 2/3 minutes. So Steve, working by himself, would take a little over an hour to do the full wall. Steve lazy. That doesn't seem like Captain America to me. A train leaving a station. When I was growing up, these kinds of problems really freaked people out. You saw them in cartoons all the time. Let's see if we can't do it a little better here. Refer to the application. No, I'm not referring to any application. Example 5. Let's move on to something else. Solve 3x over x minus 1 plus 6x minus 9. Ooh, common denominator already. Equals 6. I can just add these, right? What's 3x plus 6x minus 9? 9x minus 9 over x minus 1 equals 6. Now you'll notice that I don't yet have a common denominator everywhere. I had it on the left side, which is why I went ahead and added that side, but I didn't have it on the right side. So I guess let's get it. So let's treat that like over 1. And so we're going to need an x minus 1 over itself. And so what this gives us is 9x minus 9 over x minus 1 equals 6x minus 6, because I'm distributing, over x minus 1. And then we can just say 9x minus 9 equals 6x minus 6. Subtract the 6x, subtract the 6x, add the 9, add the 9. And so we get 3x equals positive 3, x equals 1. And you should be wondering, oh, that's great, but that's just like what we did on examples 1 and 2. So why is it coming up here at the end of the lesson? Is there anything we forgot to do at the beginning of this process? What actually happens if we plug in 1 here? It should be solved, right? It should work out to 6, but what actually happens is we get 3, that's 3 times 1, right? Over 0 plus 6 minus 9 over 0 equals 6. 3 plus 6 is 9, minus 9 is 0. Does that seem right to you? 0 over 0 equals 6? I mean, even if you wanted to tell me that you knew what 0 over 0 was, would you say that it was 6? No. What went wrong? We had an excluded value that we forgot to do. X cannot be 1 in this equation because it would cause a denominator to be equal to 0. This is what we call an extraneous solution. It's worth saying here, there is another way to approach this. Let's say we drop into our graphing calculator, and we're just going to write in the whole left side of the equation. Y equals 3x over x minus 1 plus 6x minus 9 over x minus 1. You'll notice something a little strange happens. What's going on here? It's just a horizontal line all the way across. If we typed in the other side of the equation, y equals 6, are these two lines ever going to intersect? No, they're not. Something weird is going on here. If you go into the tables, you can see, oh, that's interesting. Part of the weird thing that's going on here is that although this does appear to make a horizontal line, it's undefined at 1. And so there should be no way to plug in 1 even if I wanted to, but it definitely wouldn't end up equaling 6. And so that's why we have to check for extraneous solutions. We have to make sure that we exclude whatever values we need to exclude. I bet you guys can do the check your progress problems yourself. I'm going to let you off early. No.